Okay, so let's talk a little bit about Chapter 5 and see how this goes. Just a quick overview really quickly of Chapter 5, and then we'll try a few problems. Chapter 5 is about inner product spaces. We just started it this past week, so there will be more to say about it, but I'm going to give you the quick overview of it right now. Make sure that you know the axioms of an inner product. This is very important. So the axioms of an inner product, this is, we listed them. There's, how many axioms were there? There's 4 of them, right? Yeah, and this is what you're working on some problems on already. So the inner product of a vector with itself has to be at least 0. And it equals 0 only if x is 0 itself. That's the first axiom. And then the second axiom is the inner product of x with y has to equal the inner product of y with x. I want everybody to know that. The third one is that you can pull constants out. So if you have a constant in front of one of the vectors in one of the positions of the inner product, you can actually pull it out. Here, the constant is appearing in the first slot of the inner product notation, but if the constant was in the second position, you can also pull it out in the same way, right? We talked about that. And then finally, if we had like x1 plus x2 comma y, that thing can be broken up as the inner product of x1 with y plus the inner product of x2 with y. So you can break it up in this fashion here. Okay, so make sure you know these axioms. I might give you a proposal. Here's a proposed inner product. Does it work or not? And in that case, you would need to run through these axioms. Usually, the first one is most important to think about because it's usually easy to verify the algebraic axioms down here. But the first one can sometimes go awry depending on what your proposed inner product is. So you have to be a little bit careful of that. Once you have an inner product in your hands for your vector space, then we can start talking about things like the length of a vector, right? The magnitude. So make sure you know how to find the magnitude of a vector. A unit vector. The unit vector is always just obtained by dividing a vector by its norm, whatever that norm is. Oh, by the way, the formula for the norm here is just the square root of the inner product of the vector with itself, right? That's the formula. So this is equal to that. Unit vector, we also have the angle, theta. This is always the angle between two vectors. You just take the inner product of the vectors, let's say v and w, and you have to divide by their norms, multiplied together on the bottom. Okay, so that's the angle between two vectors. Okay, and so you can start calculating some of these geometric ideas here. Then we have the ideas of orthogonal and orthonormal sets. We started getting into this towards the end of class on Wednesday. And so an orthogonal set just means that any two of the vectors have an inner product of 0. Vi and Vj have an inner product of 0. And orthonormal just means that every one of the vectors in the set also has a magnitude of 1. So you're looking at a bunch of unit vectors. So this is the idea here. Okay? So far, this is what we've talked about up until now in Chapter 5. There's one more thing that we're going to talk about, and I'll just mention it now so you're getting it ahead of time in your list of things to think about, is something called the Gram-Schmidt, you didn't get to this yet, the Gram-Schmidt orthogonalization process. It's the Gram-Schmidt orthogonalization process. So let me just explain kind of what I'm talking about. If I give you some vectors, let's say v1, v2, v3, and so on, usually I won't give you more than 3. Those vectors might be anything, any vectors whatsoever. What I can do is I can apply this Gram-Schmidt process to it. I'll just put Gram-Schmidt over this arrow and replace this random set of vectors with an orthogonal set, which is written, I'm going to write them, you'll see me do this on Monday, I write them as W's. So W1, W2, W3, and so on. So this is, what we're doing when we do this, is we're replacing this kind of random set of vectors with an orthogonal set of vectors. And we're doing it in such a way that the new set of vectors still spans the same thing that the old set did. I'm not just going to take these vectors, throw them in the garbage, and start over. No, I'm going to take these vectors and massage them so that they still span the same thing that the original vectors do, but they are mutually perpendicular. And then, of course, the next step, which would be optional, would be the normalization process. So if you're only looking for orthogonal vectors, this is it. You stop right here. But if you actually want orthonormal vectors, then you would normalize that set and you would write down your answer as U1, U2, U3, and so on. Okay? The normalizing step is easy because all you're going to do there is you're going to write UI as VI divided by the norm of VI. So you just have to normalize the vectors. You kind of already know how to do that. You just take your list of vectors. Actually, these are W's now, aren't they? Sorry. This should be WI divided by the norm of WI. So you just take your vectors in this list and you go one by one, you divide by their norm, and that makes them into unit vectors, right? That's going to create unit vectors out of those. So you can start with a random set, orthogonalize it first using this process that I haven't explained yet, Gram-Schmidt. And then once you have an orthogonal set, you can then proceed to normalize that set of vectors. So that's the rest of chapter 5. It turns out that there are nice formulas. I will on Monday want to derive them for you, but there are nice formulas for these W's. And I'm even going to give them to you on the test. You don't have to memorize them. It's very simple. I'm going to write them down right now just so you'll recognize them, but it's very simple. The first vector W, the W1 vector, is just V1. You just keep whatever the first vector was originally, that's going to be the first vector of your new set. And then W2 is V2 minus, you have to do a subtraction here. So you take the second vector from the original set, you take the inner product of V2 with W1, and you divide by the norm of W1 squared, and then multiply by W1. Again, I'm going to give you this formula on the test, and I'm also going to explain it so you'll understand it on Monday. Okay? And then finally, W3 would just be V3 minus, well, I take the inner product of V3 with W1 and I divide by the norm of W1 squared times W1, and then minus another term. Gets more complicated as you go along. The next one is the inner product of V3 with W2 divided by the norm of W2 squared all times W2. So, and then it keeps going, but I don't think I ever, in the 18 years I've been teaching this class, have ever asked for more than 3 vectors. So this is a pretty good bet, okay? Magically, the W1, W2, and W3 will now be orthogonal. Okay, they will end up being orthogonal. And so, from there, you can just simply go ahead and normalize them if you are asked to do that. So, great. I don't actually have any problems on this review sheet from chapter 5. I just noticed that. That's kind of weird. Well, I can make something up very easily. Let's just do a couple of problems just to practice a little bit. Yeah, so let's do an example here. Let's do an example. This would be a perfectly good test question. So let's do this. Let's use the inner product of f with g equals to the integral from 0 to 1 of t, f of t, g of t, dt. By the way, I might ask you to verify that that is an inner product. In class last time, I showed that the integral of f of t, g of t is always an inner product. It satisfies these 4 axioms. If you put this extra t in here, as long as you integrate from 0 to 1, you'll be fine. On Wednesday, I tried to change the limits. I don't know if you remember my example. On Wednesday, I integrated from -1 to 0, and that did not work because you could get an example where the first axiom fails. But this one is going to satisfy all 4 of those axioms over there. Okay? So let's do this. Let's find an orthogonal basis for the span of 1x and x squared. In other words, let's find an orthogonal basis for P2 of R. The span of 1x and x squared is just P2 of R. So let's see if we can do this. If you see a question like that on the midterm, which you probably will, find an orthogonal or find an orthonormal basis for something, it's almost certainly an application of this Gram-Schmidt process that we're talking about. So we can assume that that's what we're supposed to use. Okay. So let's try it. You guys ready? Let's do it. I'm gonna call the first vector v1, the second vector v2, and the third vector v3. So this is my original set of vectors. It might look like a really nice basis for P2 of R, but as it turns out, it's not an orthogonal one. Right? It's not orthogonal, and that would be easy to verify by just taking the inner products of these vectors. You won't get 0. Inner product of the first one with the second one, not 0. Inner product of the first one with the third one, not 0, and so on. Right? So what I'm going to do is I'm going to, for the solution here, I'm going to start using my formulas for these w's instead. So the w1 is just going to be 1. Okay? According to my formula, w1 is just v1. Okay. Now the next one is w2. What's the formula there? Well, we take v2, which was x, and we're going to subtract some multiple of w1. So it's the inner product of v2 with w1. That would be the inner product of x with 1. divided by the norm of 1 squared, sorry. The norm of 1 squared. Okay. I think to keep it kind of clean here on the side, I'm going to do some scratch work and try to calculate these things. So the inner product of x with 1, let's just work that out over here on my scratch paper. You know how to do it? I pretty much gave you the formula. It's right here. The inner product of two things, you're just going to use this integration, right? So I'm going to integrate from 0 to 1 of what? T times f of t. Well, my f is this thing here, x. So that's just going to be another t. And then the g of t is a 1, and then dt. So I'm just going to be integrating t squared, which is what? 1/3 of t cubed? 1/3 of t cubed evaluated from 0 to 1 gives me 1/3. Alright, so I've got that figured out. Let's figure out the norm of 1 squared. So this would be the inner product of 1 with itself, right? The norm of a vector is just the square root of the inner product of the vector with itself. And you square both sides of that, this is the equation. So we're going to do another integral using the formula on the top left up there. So I have to integrate from 0 to 1 of what? T times 1 times 1, right? T times 1 times 1. So you're just integrating t. Just t squared over 2, right? So just get t squared over 2, we evaluate that from 0 to 1, and it comes out to 1/2. If I did it right. Okay. Amazing. So we've got that. So let's come back and plug those numbers into here. So we have x minus, well, this is a 1/3 on top and a 1/2 on the bottom, right? So what does that reduce to? X minus 2/3, right? So that's W2. That's my second vector. And now this vector should be orthogonal to this one, right? If I take the inner product of these two things, I better now get 0. Otherwise I mess up. These have to be orthogonal if my formulas are correct. Yeah, Kevin?
And we can use x and dx instead of t's, or?
Yeah, if you don't want to switch it to, I mentioned in class that I like to just switch to the dummy variable of integration, which is, for me, is t is easy enough to use. But if you want to leave it in terms of x's, that's fine. Yeah. Is everybody understanding this? Let's do the last one real quick, W3. It's a little tedious. I will give you that. This is kind of tedious, but it's not conceptually that bad. You just have to be willing to suffer through the equations here. Right? So W3, we start with V3, which is x squared. And we're going to subtract the inner product of x squared with W1 and divide by the norm of W1 squared and multiply by 1. And then we're going to have another term, according to the formula. I also have to subtract the inner product of x squared with W2, which we just determined was x minus 2/3, divided by the norm of x minus 2/3 squared times x minus 2/3. So I'm going to clean up my scratch work here so that I can do this. Simplifying this is a little bit tedious. I'm going to have to calculate, well, I already know the norm of 1 squared. That was 1/2. We had done that earlier, right? That's on the bottom here. But I have to do this inner product here, the inner product of x squared with 1, which will be the integral from 0 to 1 of t times t squared times 1 times dt. That comes out to 1/4. So you integrate t cubed, you're going to get 1/4 of t to the 4th. Thank goodness the limits of integration are 0 and 1. That keeps the numbers somewhat nice to work with. Agreed? following what we're doing here? Let's do on our scratch work, let's do the inner product of x squared with x minus 2/3. Let's figure out what that would be. So for this one, I integrate from 0 to 1 of t times t squared times the quantity t minus 2/3. So I just have to do an integral. It's just a little bit of work. Let me simplify it before I actually integrate it here. So this is actually the integral of t to the 4th minus 2/3 of t cubed. Okay. When I integrate t to the 4th, of course, I will get 1/5. And when I integrate t cubed, I will get 1/4, but I'm multiplying that by 2/3. So 1/4 times 2/3 is 1/6, I believe. So that should be minus 1/6 if I did it right. And so that gives me 1/30. All right, and finally, I have to figure out the denominator of this part. So I have to figure out the norm of x minus 2/3 squared. Let me do that one over here so that I keep it on the screen for the camera. Okay. Yeah, so this is the integral from 0 to 1 of, what is it? T times t minus 2/3 squared dt. Oh, this is going to be a little bit annoying. So this is the integral from 0 to 1 of, well, if I FOIL this out, I'll get a t squared times a t, which is t cubed. And then minus a cross term here would be 4/3 of t squared. And then the constant term would be 4/9 of t. So this is going to be the integration that you have to do. Did I do it right?
Plus 4/3, right? Negative 2/3. Oh, no, never mind. I'm sorry.
I think it should be a minus here and a plus here. Yeah, will look okay? Okay, great. And now I just have to integrate that. This is going to be 1/4 for the first term. The second term, when I do the t cubed over 3, I think is going to be minus 4/9. And then when I integrate the last term, I think it's going to be plus 2/9. And so it's just some messy fractions. If I put 36 on the bottom of that, I'm going to have 9/36 minus 8/36, I believe. So it comes out to 1/36. All right, so I can get my third and final vector, W3. It's x squared minus, let's start putting all the numbers in. The inner product of x squared with 1 was 1/4. The norm of 1 squared was 1/2, that's times 1. And then minus, we have 1/30 over 1/36 of x minus 2/3. And that could probably be simplified a little bit. This is going to be x squared, and then the x term, this is actually 6/5. 1/30 over 1/36 is actually 6/5, so that's going to be minus 6/5 times x. And then I got to figure out the constant term. Wish me luck with that. 6/5 times 2/3 is 6/5 times 2/3 is 4/5. So this is 4/5, but then I also have to subtract 1/2, right? 4/5 minus 1/2 is 3/10, I believe. 4/5 minus 1/2 is 3/10. So there you go. Your final answer, the final answer for the orthogonal basis would be 1 x minus 2/3, that was the W2. And then finally W3, which we just worked out, x squared minus 6/5 x plus 3/10. So that takes a little bit of work, but conceptually it's not too bad. Conceptually, it's not too bad. Does this make sense, guys? Are we understanding it a little bit? Okay. What's that? Oh, did I say orthonormal?
No, I just said.
Oh, I said orthogonal. Oh, I could follow up. Actually, it's weird. This vector would not be normalized yet. We would have to divide this one by its norm. The norm of the number 1 would be the square root of a half. So actually, you would be replacing this one with 1 over the square root of a half, and the answer to that would be square root of 2. So you can get weird things depending on what, it all comes down to what this is. I could change this t to, I could change this to t squared right now, and we'd have to redo the whole problem. It'd change everything. All the numbers would be different. Okay. This is the Gram-Schmidt process. You guys already have a leg up now, and that's what you're going to be doing some examples on for Thursday's homework. Let me give you one more problem right now that we can talk about, and then I think I'll call it a day, if that's okay. I'm going to wait, and I've got some problems from chapter 6, but I think we haven't covered that yet, and instead of trying to teach chapter 6 now and then reteach it on Monday, since I moved the exam back, I feel a little bit okay to just wait until Monday to explain that, and then I can go over these sample problems from chapter 6 at that point. But let me give you one last example and tide you over for the weekend. Okay? Suppose that the set U, V, W is an orthogonal basis for some vector space V. I don't even have to have it in mind. Some inner product space V with the norm of U equals 1, the norm of V equals 2, and the norm of W equals 3. What I would like to do is compute the norm of 4U minus V plus 2W. Let's see if we can do this. This will not take as long as the last one. It's definitely faster. So first thing is, make sure you understand this is a number. We're calculating a number right now. We're calculating a number here. To think about what kind of a number that is. So can somebody suggest, how do we calculate a norm of something?
Take the square root of this product.
Right, it's the square root of the inner product of this vector with itself. So exactly, we need to calculate the square root of the inner product of 4U minus V plus 2W with itself. 4U minus V plus 2W. This is what we're going to have to calculate. Okay? So, all of the action is going to be underneath the radical. It's all going to happen underneath the radical. I just keep drawing this radical every single step. Okay? What can I do underneath this radical here? Well, I'll plug values in a little bit. I mean, I've got some numbers here I'm going to begin to use, but I'm not quite there yet. What were you saying, David?
4U, 10, 4U.
Okay, we can break this up. Those axioms of an inner product that we mentioned at the beginning allow us to sort of FOIL this out, right? So we get the inner product of 4U with 4U, and then minus the inner product of 4U with V, and then plus the inner product of 4U with 2W, right? And then I have to keep going. I have a lot of terms here. Minus the inner product of V with 4W. This is a V right here. and then plus the inner product of v with itself, and then minus the inner product of v with 2w, and then
Just foil it?
I'm foiling it, yeah. And this is allowed because the axioms of an inner product tell us that the inner product respects addition and scalar multiplication. So I'm just foiling this thing out, okay? The last three terms are coming up right here on the bottom, 2w with v, and then finally the very last one is the inner product of 2w with itself. All of that is under this ginormous radical. Okay. Okay, so now what?
Coefficients?
Okay, the scalars, the 2's and the 4's and so on that we see, is that what you're talking about?
Yeah, but could
What
we
can you
just-
do with those?
You can
Say
take
again?
them out.
I can take them out. Yeah, I can take them out. So like right here on the first term, 4 times 4 is 16 times the inner product of u with itself, right?
Would you have to though, or like does
No.
that reduce your work?
It is going to be a good idea to pull that out. You're going to want to pull that out. So that's this one. What about this one here? Okay, so that's going to be minus 4 times the inner product of u and v, but I have a question. Do we really have 9 terms here that we're going to have to deal with? Why not? Why is this not so terrible as it might look? Well, I can't really combine anything. I guess these two could be combined. They're the same, right? And these two could be combined into one. So there's some ways to combine them. But what's the really fast thing that I should try to take advantage of that's going to wipe out almost everything here? There's one word on the board that we need to look more closely at. The word orthogonal. To read these questions very carefully. If vectors are orthogonal to each other, what is their inner product going to be equal to? 0, right? So here you go, u and v, they're orthogonal. This is therefore 0. U and w, 0, right? V and w, 0. Now here's a term that we can't cross off. This, the inner product of v with itself, I'm going to recopy that one. Okay, but the next one, v and w, that's 0. W and u, 0. W and v, 0. The last term, I have to keep that one. There's 2 factors of 2, which makes 4. And then the inner product of w with itself. Okay, so this is what we should end up with now.
Sorry, but
It's okay.
alright. So basically, they're orthogonal because
Well, that we were told that these were orthogonal. In the original problem, they told us that u and v, u and w, and v and w, these are all orthogonal, so these inner products are all 0. Right? That's given. It's a slippery little thing. It's actually the difference between getting this question right and getting it wrong is just reading the question carefully. The vectors are orthogonal, so 6 of these 9 terms just wipe away immediately.
oh, so that's telling you if it's unless it's crossed with itself,
It's 0.
Okay.
Yeah, right. So any two of them are 0 if they're different. The only ones we have to keep are where they have the same vector in both slots. Okay, so now help me out. What am I going to do next? 16 times. What is the inner product of a vector with itself? That's called the norm of the vector squared, right? Okay, so we have that, and then we have the norm of v squared, and then 4 times the norm of w squared. That's really what you're looking at underneath that radical. Great, and so now we can start plugging the numbers in, because we were given these numbers. 16 times 1 squared plus 2 squared plus 4 times 3 squared, right? And now we're gonna get a number pretty quickly here. This is gonna be 36 plus 20 square root of 56. Does that look right? And that would be the answer. Square root of 56. Okay, square root of 56. So I like these kind of problems because they use the inner product axioms, and it's a nice chance to review what orthogonal vectors means. And just knowing the basic definitions, you can solve these kind of questions. And so I just thought I would throw one of these at you. I think there's another one or two in the homework that you're going to be working on, but that's about it for now on that. So what did I not cover today? I just want to say a couple quick things. I didn't talk about chapter 6. I'm just going to wait because I want to just cover that on Monday, and then I can probably take some of these review session questions and either put them into a group work or just do them as examples during class. So that's that. And then the other thing that I didn't really do a lot on today was verifying axioms of an inner product and so on. We had done quite a bit of those on Monday, or on Wednesday, I mean, in class, and we're going to get more practice on that as you start looking at the sample test and so on. So I kind of feel okay about kind of calling it good with what we've done. We've done a lot. We've done a lot, and we've even gotten a head start on the Gram-Schmidt. I didn't explain the formulas yet. I'll do that part on Monday, but using them to solve the problems is what you're really going to need to be able to do anyway. So, all right. Anybody have anything else they want to ask me before we call it a day? I am going to go down to my office, by the way. I have office hours right after class, or right after the review, so you can also talk to me there.
Yeah, a column.
Mm-hmm.
Even if
Orthonormal vectors would have a norm of 1. These are just orthogonal vectors. Yeah, if this had said orthonormal, then I wouldn't have given you these values, and I would have just expected you to know that those were all 1. In which case the answer would have been the square root of 21. So that would be a slight modification to this problem. That's true. All right, great guys. Thanks for coming today. I'm going to turn this thing off. Thanks for watching, guys.